So hello. Today I'm going to give you a brief introduction to Coq. So here is my name, here is my company, here is my email, and let's go straight to the topic. So first of all, I need to make a disclaimer. So I have no formal training in formal methods, computer science, or whatever. So some things that I will show you may be inaccurate or even blatantly wrong. So if you know something better than me and see that I'm doing some mistake, just shout from your place and please correct me. So I learned this tool using this brilliant online course. So if you like this talk, I would be happy if at least someone of you take this course as well. So it's written by quite a famous guy, Benjamin Pierce, and it's really a full-blown course about software foundation, and they use Coq as a programming language. And it's an interactive course, so you give immediate feedback about what's right and what's wrong. So it's cool, and most of my examples are either taken from this course or at least inspired by it. So what's the use cases of the Coq theorem prover? So first of all, you can do normal mathematical proving with it. So whatever mathematical theorem you can imagine, it's possible to formalize it in Coq as long as you can prove it with a pen and paper. And the most famous mathematical problem that has been formalized using Coq is the problem of coloring a map with 4 colors. So the second use case is a little bit more practical. It's proving some properties about formal systems. So imagine that you building some formal system, for example, yet another programming language, and want to prove something about it. For example, that your type system is sound, that your transformations are correct. Then you can formalize it using Coq and prove things about your system. And I heard that, for example, for Scala, for new Scala compiler, someone who works on this Scala compiler actually proves some statements in Coq about it. And the third use case, it's quite rare but still exists. You can actually write executable programs. So you can not only prove something, but you can actually make a binary from it and run. And the most famous example is CompCert C compiler. So Coq is written in French Institute INRIA, and this C compiler CompCert is written in INRIA as well. And this is a C compiler which supports the rather big part of the C standard, and this compiler is proven to be correct. So if some company works on mission-critical systems, they buy the license for this compiler and compile their programs with it. So Coq as a system is built on solid theoretical foundations. And the root of those foundations is the observation called carry-over correspondence. So when you do math, you have a world of theorems. So you have a theorems and proof of the theorems. And in a world of programming, you have types, in most cases. And you have values of those types. And this correspondence says that if your programming language is powerful enough, then for each theorem, you can pick a particular type in your programming language. And as long as you can find a value of this type, if you found it, that it means that the value of this type corresponds to a proof of in the world of theorems in mathematics. So the workflow when you work with theorem provers, not exactly Coq, but in general. So you pick a proposition, Then you describe this proposition as a type in some programming language. Then you try to create an instance of this type. And when you actually found the instance of this type, this proposition is considered proven. So I will show you examples of it. So that's a list of most important features of Coq. So it has a powerful type system based on dependent types, which are actually powerful enough to describe almost all mathematical statements that you can imagine. And of course, any properties that you can imagine in your in the real world programming. So also it has a tactics. It's a kind of syntactic sugar to make your Coq programs look more like mathematical proofs. Also, it has a feature of proof search. So, for example, when you try to prove something, you most probably will stumble upon some facts which are quite obvious themselves and most probably proven by someone. And with Coq, you can find the proofs if they exist in some libraries or Coq standard library or in the code that you have already written. And then finally, you can take a Coq program and compile it. But Coq doesn't have a compiler to some binary code by itself. Instead, it uses extraction. So it takes source code in Coq and then translates it to source code in another programming language. So most mature implementations of extractions extract to either OCaml language or to Haskell. Okay, let's do some code. So Coq is shipped together with its own IDE. So here it is. So the screen consists of 3 parts. The first is actually a text of the program. The second is a window for messages. And in the upper corner is the place for proofs. So let's start with something simple. Let's define a Boolean type. So with this IDE, you can write a code, and the IDE will check for correctness just on a way. So I written a definition of Boolean type. So word inductive, just forget about it for now. Then bool is a name of the type, and we say that bool is a type. And it has 2 possibilities. It's either a Boolean as either true or false. If someone is familiar with OCaml or Haskell syntax, it should look familiar. If not, then it's like enum. Okay, the next step. Let's define some function of on a Boolean. The most simple function that you can imagine is negation of Boolean. So for true, negation of true is false. For false, negation of false is true. Here it is. So definition, it means we are declaring function, then a name of the function, then type of the input argument, and then a type of the result. Since Boolean has 2 possibilities, true or false, to define a function on Boolean, we must provide the result of this function on both cases. So we are doing exactly that. We say match the argument and then consider both possibilities. If it's true, we return false. If it's false, we return true. Okay, then with command print, we actually can print this definition, and you see it in the bottom corner. Okay, then Coq has a compute command. So you can take an expression and evaluate it. So we evaluate negation of true, and see that it is false as expected. Everybody can see, I hope, it's in the bottom corner. I think I can even make it a bit larger. Okay. Then the next important command that we will often use today is check. Print command prints the definition of something that you created, and the check command just writes the type of it. But the type is kind of most important part of everything here. So it says that function necb has type bool, arrow bool. So it means that it takes one argument of type boolean and returns you a boolean. Okay, let's continue with a couple of a little bit more complicated examples. So now we define function and function or. So just logical and logical or. But the difference is that they, of course, need two arguments. Again, we take the first argument, match on it. So if it's true, then we return the second argument. If it's false, we immediately return false. The same way we defined or function. Okay, let's check that it makes sense. Yeah, of course, true or false returns true. And let's check the type of it. So the type. So if you have no experience with functional programming, this type can look a little bit scary. So strictly speaking, it says that it takes one boolean and returns you a function that itself takes one boolean and returns you a boolean. But in fact, it's morally equivalent just to a function which takes two arguments and return you a boolean. So it's called carrying. So if you know it, that's great. If you don't know, you can just look at the rightmost arrow and consider everything that comes to the left of the rightmost arrow as a list of arguments. And what comes to the right from the rightmost arrow is the result type. So function or b takes two booleans as an input and returns you a boolean as an output, as you expect from a normal or function in logic. Okay, so we printed the type of check, type of or b function, but what happens if we supply only one argument, or be true? So if we take a function of two arguments and apply it to one argument, we get a function of only one argument. So the first argument is set to true, and as a result, we have a function. This is called partial application. Okay. And if we submit both arguments to or b function, we get a result, boolean. So the type of expression or b true true is boolean. Okay, so let's now prove some simple facts. So I declared a theorem. So its name is test and b, and the statement of the theorem is that if we apply function and to true and true, the result will be true. So it's the most simple theorem that you can imagine. Then we enter a proof mode. So you see that this statement that we want to prove appeared in the upper right corner. So what we can do with it? So I said that Coq has so-called tactics. So it's a kind of syntactic sugar which makes your program look more like mathematical proofs. So we apply the first tactic, simple. It means simplification. So it takes the theorem that you want to prove and tries to simplify it as much as possible. So you see now it's and b true equals to true. Then I push the button and it will be simplified. So in and b function, it knows both of its arguments, so nothing can stop coq from applying this function. Okay, now this fact looks trivial, and to prove facts like that, like a equals to a, there is a tactic called reflexivity. Okay, we have proven this fact. Okay, sorry. Okay, next example. So it's basically the same, but now we take a little bit more complicated expression which involves both and or operations. Again, on the left-hand side of this statement, we have just a couple of functions with all arguments applied, so we can just evaluate it using a simple tactic. Again, we get, as a result, we get some trivial statement, and we solve it with reflexivity tactic. Okay, done. Okay, so now a little bit more complicated example. Sorry. So theorem about that if you have a function and the second argument you submit to true, then the result is the first argument. So the main difference with the previous theorem is that here the previous you had all arguments known, and here you have an arbitrary variable b. All you know about this variable is its type, bool. So you can see that a statement that it involves keyword for all. It means that this statement has to be true for all values of b of type boolean. Okay, so here we have one new tactic intros. This means introduction. See, before applying this tactic, we have original statement, and then after that, variable b comes above this line. So when you deal with a proof mode in coq, so your state of your proof looks basically like that. So you have a line, then below the line you have a statement that you want to prove, and above the line you have all assumptions that you have and that you can rely on. Currently we have only one assumption: the type of b is boolean. Okay, let's try to solve it as before. Let's apply a tactic simplification. But you see that it doesn't change the goal of our proof at all, because if function end doesn't know its first argument, then it can't simplify the expression. So to solve it, we have to consider manually both cases of variable b. So it's either true or false. For manually dealing with different possibilities of a variable, we have a tactic destruct. So before we had one goal, and now we have, you can see we have two goals. One for value of b equals to true, and the second equals goal where b is false. Then we go deeper, we focus on the first possibility. And here you have just a simple expression as before, and you can solve it as before with simplification tactic, then reflexivity, then we are done. Okay, go to the second case. Again, simplification, reflexivity, we are done. Okay, it looks a little bit tedious to apply manually simplification and reflexivity. So I want to show you the tactics auto. Let's prove the same fact, but a little bit shorter. Again, we introduce variable b. Again, we make a case split by variable b. But now, instead of, those facts look very trivial, and in the 21st century, no human should do those simplification manually. So there is a tactic called auto, which solves this problem just in one shot. So auto is a tactic which takes it just tries to apply different tactics and different assumptions, try to automatically prove the statement. And for very trivial statements, it works. And it saves some boilerplate.
Would also auto work if you didn't destruct B? Could you just write auto in the beginning?
No, it won't, I guess. We can try. Yeah, it's a very stupid tactic. It doesn't do any tricky things. It does either work or not. So it doesn't do any complicated search. Okay, let's do some live coding and try to prove some simple statement. So that OR operation commutes. So OR of A and B is the same as OR of B and A. Okay, let's introduce first variable. Basically, it introduced both of them. Then do case split on A. Okay, go focus on the first part when A is true. Let's simplify it. Yeah, it became a little bit more clear, but still we need to make a case split on B. Again, we have two cases, but they are trivial. And the second case, when A is true but B is false. Okay, the first case of B is done. Now the second case. Again, we can simplify it. Now we see that we need to case split on B. Sorry. Okay, and again, auto is our friend. And don't forget about adding QED. If you don't, you sometimes have very weird compilation errors. Okay, so we introduced the most simple type, Boolean, which have only two possibilities. And let's continue with some more complicated thing. So let's introduce natural numbers. So who ever heard about piano encoding of natural numbers here? Okay, great, many people. So formalization of natural numbers in mathematics, so the most widely used, is the following. So a natural number is either 0, or if you have a natural number, you can determine the next natural number after that. So here is the definition in Coq. So it's, as before, it's a type with two constructors. But before that, both constructors were just constants, true and false. And here, the first constructor is doesn't take any additional arguments as well, so it's just O, which represents 0. And the second constructor, called S, takes another natural number as an additional parameter. So the second constructor is kind of recursive. Okay, let's check the type of those constructors. So O is a natural number. It has type net. Then SO is also a natural number. And in this encoding, it represents the number 1. Then if we want to build number 2, then we apply a constructor S to number 1, which is itself is SO. And if we want to build 3, then we apply S once again. Very convenient. Okay, so this definition is the same as the internal definition of natural numbers in Coq standard library, with the only small difference. Coq standard library just pre-prints natural numbers in decimal form. So, for example, here, here I kind of encapsulated my definition, then I kind of run out of scope, and now I work with natural numbers from the standard library. And when I say check SSSSO, it prints, you can see in the left corner, 4 in a human readable format. But that's the only difference. Otherwise, in Coq, natural number is just like that, a type with 2 constructors. Okay, what happens if we run check S command? So it says that S is a constructor which takes a natural number and returns you a next natural number, is just a function. So it has a type not to not. So it's important that constructors in Coq are just normal functions that you can define manually. Okay. Let's now write some function definitions on natural numbers. So let's define addition of natural numbers. So here I define function plus, say that it takes 2 arguments n and m of type not and returns not. And I have to I have to put a keyword fixed point here, and it says that this function is a recursive function. So I'm allowed to make recursive calls inside this function definition. So as before,
generally necessary for any recursive function, you have to put the fixed point in front?
Yeah.
Okay.
Yeah. Like with booleans, if we have a data type, we have 2 possibilities. We have to provide function definition for both of them. So again, we do a case split on the first argument. If it's 0, then 0 plus m is just m. And if it's not 0, then any number greater than 0 can be represented as the next to some other numbers. And we call this plus function to a smaller argument, to the argument n prime, and then just increase it by 1. So if I removed this fixed point keyword, it wouldn't allow me to do it. Let's check it. Ah, no, actually it can.
Try to compute.
Yeah, maybe it became less restrictive. Good to learn something on the way.
So what's the difference between fixed point and definition?
So when I learned it, So definition is just a function. Fixed point is it's also a function, but you explicitly declare that you will do recursive calls. So it's a recursive function.
But you can do that with definition, right?
Now I found out that I can, but Coq is much more restrictive in terms of well-foundedness of recursion. So when we'll probably come to it later, but it's very important for all recursive functions to be well-defined. So you have to prove that all your recursive calls are actually terminate to the base case.
In other programming languages, I know it from Scala and Haskell, the fixed point is for the recursive type, yeah, and not only recursive functions, because if I have a recursive type, so I need recursion as well, but I can use recursive functions in other cases where the type is not recursive. That's much possible, but you need it if the type is recursive, and then in this case it is, yeah, you have successor of successor of successor, and you have a nested type of successor.
You're talking about fix.
Same thing in Coq, so just a question.
You're talking about fix data type in Scala here?
Yeah, for instance.
Yeah, and if you wanted to define natural numbers in the same way, probably you would need this fix data type. So yeah, it's related. So this fixed data type is related to what I'm talking about, but not exactly like that. But yeah, all this fixed point stuff comes from lambda calculus, from fixed point operator. Yeah, it is related. Okay, let's check that our function works correctly, at least for 3 and 2. Yeah. Okay, let's now define one more function on natural numbers.
Just a question. So I also learned that the way you said it, that you can't write definition for this recursive function, that you have to use fixed point. Yeah? That's also the way I learned it. But I think there's a small. Can you, in the definition of mult, can you replace fixed point by definition?
Let's try.
And look at the message. Yeah, here it just says it's defined, and with fixed point it also checks that there is a proper recursion. Yeah, I mean, I'm just not using it. But I agree with you. The way I learned it is that you cannot use definition for.
Yeah, probably. Yeah. Just it became more relaxed and try to infer something. Okay, and here's actually an example that Coq cares about well-definedness of recursive function. So here I try to declare a function called bet, and in the second line I try to call this function on a larger argument than the original input. And it vocally complains in the left corner, you see. So it says that the recursive function is bad or ill-formed.
What happens if you write definition here? Does it
I guess even worse. Yeah.
Ah, yeah, okay. So it's a good idea to use fixed point.
Okay, so yeah, it's a very important point. So if you do normal programming in even in Haskell or Scala or other typed language, if you accidentally created a function which doesn't terminate, it will crash at runtime or doesn't terminate, but at least it will signal about an error in runtime, and you go and fix it. If you allow recursive function without a proper termination in coq, then you basically can prove any theorem. And it will just silently accept wrong proofs. So for soundness of this system, well-definedness of recursion is crucial. Okay. Now we are ready to actually prove some properties about our data types. I defined a very simple property called even, which is meant to define if a particular natural number is even or not, if it divides by 2 or not. So it's a data type which accepts a natural number as a parameter, and as a result it gives you a proposition. Proposition is just a type, basically. And as before, this data type has a couple of constructors. The first constructor is called, I don't know, 0 is even. It's just a fact that we consider 0 to be an even number. You see, this is the name of the constructor, and it results with a value of type even 0. That we consider 0 even. And the second constructor of this property, we call it plus 2 is also even. It takes, it basically says that if we have an even number and we add 2 to this number, then the resulting number is also even. So it accepts any natural number. Then it accepts the proof that this natural number is even. So we remember from Curry-Howard correspondence that if you want a proof, we want actually an object of the type which corresponds to this fact. So even n is an object, just normal object from our programming languages, which corresponds to this property applied to the number n. And as a result, we have a proof that n plus 2 is also even. Okay, sorry.
So the second one is the recursive invocation, and the first one is this even n in parentheses. That is an object, you called it. I did not really understand it. So.
Even n is a type.
Is a type.
Yeah. So we are working with dependently typed language. So our types can depend not only on types, but on values as well.
Yeah, dependent types.
Yeah. So we need to provide, so to use this constructor, we first have to tell it the natural number and a proof that this natural number is actually even. Yeah. Okay, let's.
This inductive, I see this is an induction because we have a base case and then we have an induction case, and then you always have to put the inductive keyword there, or how is that?
That's interesting because inductive. We will talk later about what the inductive keyword means. But I thought I just tried to Google for probably it's possible to define in some cases just a data type without inductive keyword. But I think it's either impossible or just nobody use it, because when you call it inductive, you get lots of useful stuff for free.
So the line with +2 underscore even, the end of the expression even SSN, is it increasing or decreasing? Increasing.
So you take the proof that n is even, and as a result, you get a proof that n plus 2 is even.
Yeah, but how does it terminate?
Sorry?
How does it terminate? I mean, like, let's say I want to prove if, let's say, 8 is even, and then it expects, well, then it is gonna give me, I don't know, a proof of. Well,
Sorry. Let me clarify. It's not a theorem. It's what I personally think the even means. So currently it has no relation with division by 2. I just personally say that even is either 0 or some other even number increased by 2. It's my definition.
Okay.
You can criticize it.
It might not be the same kind of evenness which.
Yeah. We could potentially prove the equivalence of those two definitions, but now I just axiomatize what I think.
Do I understand correctly that here you are defining the type, yes, and then a function by this type, but it's not for runtime, but this function goes into the type checker.
Sorry?
This function that you have, or like you have a case on 0 and the other, like it looks very much like a function, but this information, like whatever I should call it, it goes into the type checker then. It does, this property will then apply to the types that you're introducing into the system. No, it doesn't make.
Okay.
Where is this executed or checked? Maybe it's easier question.
It's not okay. If you managed to construct this type, that it's just correct by construction. Okay. Let me give some examples, and if it's not clear, let's talk about it after those examples. So, okay, even itself is not a proposition. It's a predicate. To make it a concrete proposition which can be proven or disproven, you need to provide n, the exact number what you want to check if it's even or not. So, the type of even 3 is indeed proposition. Yeah, you can prove or disprove it. The type of even itself is not a proposition, it's a predicate. It requires a natural number to become a proposition. Okay, let's run check on the first constructor of this proposition. It has type even 0. So it's a proof that 0 is even. So what is the type of the second constructor? Second constructor is actually a function of 2 arguments. First argument is a natural number. The second number is the proof that it's even. And as a result, you get a proof for increased by 2. Okay. And we also can partially apply this function to a particular number. So if we call plus 2 even for a particular number 4, then we already submit the number, and all is left is to submit the proof that 4 is an even number.
But it says here as well that 6 is an even number, yeah? So if you want to prove that 6 is an even number, you pass 4 as an argument, and you get a proof that 6 is an even number.
I need pass 4, and the proof that 4 is an even number itself. Yeah, and then as a result, I will get a proof that 6 is an even number.
It only works in one direction. If you know that 4 is even, then you get the proof that then 6 is also even. It does not work the other way around, because you would have to know that it is.
I think in this case, just assume that 4 is an even number. Could also write 3 in there, I think. And then you would have something that proves, if you assume that 3 is an even number, then it would show that
Yeah, yeah, yeah.
So we're working upwards, and our proofs will go downwards.
Yeah, yeah, it's a very good example. I can say that check plus even 3. So 3 is not even number, but if you somehow manage to submit me this proof, I could prove that 5 is an even number as well. Thank you. Okay. Yeah. Okay. So, for example, I want to prove that 2 is an even number. I take this function plus 2. I submit 0 to it, and the proof that 0 is even. Yeah, and you can see in the bottom corner that as a result I get an expression of type even 2. Don't worry if it looks scary, it's normal. And if I want to prove that 4 is an even number, I copy-paste the proof that 2 is an even number from the line above and apply the function plus 2. And as a result, you can see I get the proof that 4 is an even number. But of course, nobody do those tricks. For proving, we shouldn't normally manually construct those proof objects. We should use proof mode and use tactics. So let's now prove that 8 is an even number, but in a more simple way. So we are entering the proof mode, and you see that we have a goal that 8 is an even number. Then I apply the apply tactic that try to prove this statement as the result of the function plus 2. So it takes what we want to prove, takes the function, and asks us to supply arguments that match the goal. So if you want to solve to get value of even 8 by as a result of a plus 2 function, we have to provide the value of even 6. Okay, the same. If we want to have a value of type even 6 as a result of a plus 2 function, we have to provide the value of even 4. I click, yeah, even 4. Then
I would put it differently. If we want to prove that 8 is even, then it's a physics to prove that 6 is even. And then next step shows if you want to prove that 6 is even, it is sufficient to prove that 4 is even, and then so you go downward. So I think I usually understand the applied tactic better this way, that it goes backward.
yeah, it goes backward. It takes the goal and asks us to prove the leftovers.
Yeah.
Okay, we go down to 2, and then when it comes to 0, we apply the base case. Done.
Can you show what happens like with 7, 9, or
like
not even?
Okay, yeah, very good question. Yeah, let's try. Even 7. Okay, it asks for even 5, even 3, even, but now we are stuck.
And the reason why we are stuck is that there is no like action what we do when there is 1, right?
Yeah.
Because 1 is not the successor of the successor of the natural number. Therefore, it can't go.
Yeah.
No, but it just says we cannot prove that 7 is an.
That's the point.
Yeah,
You
we
just
cannot
can't.
prove that 7 is
You
an
cannot prove it
even number.
because you do not have to prove for it one.
Yeah.
If you
We have not proven that 7 is not.
Yeah, we will come to this.
Quick question. If if you wanted to prove that 1 million is even, does it mean you have to put apply 500,000 times?
Yeah.
Is there a shortcut method?
Yeah, there is a thing like tactical, so it's some thing on top of tactic. So you can say, for example, that I want to repeat this tactic until it stops to succeed, but it's beyond the topic of the current talk, and it's not the most beautiful part of the COC. But yeah, it's possible to automate the thing even further. Okay, but what happens if we prove this theorem that 8 is even? In the bottom corner, you see that it's just the same ugly expression that we built manually, but not for 8, but it looks exactly the same as such proof for even 4 or even 2. So when you prove something in the proof mode using tactics, instead of manually combining function and as arguments, as a result, underneath, you get exactly the same as you would get manually applying those constructors. So tactics, it's not a separate world, it's just a syntactic sugar over applying function to arguments. Nothing more.
Wouldn't you try if you leave this, change this theorem to 6 instead of 8, but you leave the body as it is?
Okay, then it will fail in this step. So
yeah, and if you do it with 10 and leave the body as it is,
then it will fail here.
the last,
Yeah.
in the last kind of match. Yeah.
Okay, let's prove that 8 is even once again, but now I will show you the tactic called constructor. It's basically the same, but if there is only one constructor that you can apply, that it picks it automatically. So, for example, if we want to prove that 6 is even, there is no point to try to apply constructor that 0 is even. It just doesn't match. So it just picks +2 constructor. So the benefit that you don't need to remember those long names of constructor. Okay, just to your question about the fact that we failed to prove that 7 is an even number, but didn't disprove it. Okay, let's now state a theorem, kind of a negative fact. So, theorem that 5 is not an even number. So here I use the keyword from COC, not. Okay, let's try to prove it. First, I use tactic unfold, which actually shows me what this not actually means. I say unfold not. And as a result, you see, I get the function from that what I want to disprove to something called false. So it's actually a fact from Curry-Howard correspondence. If you want to disprove some fact, you need to build a function from this fact, from this type, to an empty type. I will tell you what it means. Okay, now I run tactic called introduction, which puts this even 5 about the line. So I have it as an assumption. Okay, then we have a new tactic called inversion. So I have a proof that 5 is an even number. How could I prove it? So we have only two possibilities when the number can be even. It's either 0 or it's a successor of another even number. And the tactic inversion just just rolls your proof backwards. So the only way how we could prove that 5 is even is by proving that 3 is even. It discriminated the case that we could prove that 5 is even because 5 is not 0.
So what exactly is inverse?
Huh?
What do you inverse? Like why is it called inversion?
To step back to show the inversion, just inversion, not like step. Yeah, this.
One sub goal. Well, that's a hypothesis that even is that 5 is an even number, and n is an even number. Well, you use.
Okay, there is too much garbage on the screen, so I suppose that I remove it with this tactic. So the only way to prove that 5 is an even number is by proving that 3 is an even number, because we have only 2 constructors for this data type.
So
and
you introduced yet another hypothesis H1.
I don't introduce it. Cox created it for me.
It's the only one available.
Yeah.
If you would have multiple constructors, you would most likely get multiple matching.
Is it the same thing like you do at school?
Yeah, exactly. Yeah, it's just backward thinking. Yeah.
No, I wouldn't say that it's proving the opposite. It says I find this inversion tactic also quite difficult to describe. So we have a constructor that says if n is an even number, then the successor of the successor of n is an even number. And inversion says try to invert the constructor that constructs 5.
From increasing
Yeah.
to go
Yes,
decreasing.
and then it says, okay, if I find the constructor for even 5, namely even 3.
Okay. So this is a definition of our predicate even, and all potential values of this predicate are mentioned in the right side of the constructor. So it's even 0. It's one possibility. Or it's even for some successor of another number. So if we want, if we have an even 6, value of type even 6, so it could come from here, but it couldn't because 0 is not 6. Or it could come from here, but in this case, it could be created only when we have those 2 arguments. Particularly, to get value of type even 6, we have to provide value of even 4. So inversion tactic takes even 6 from here and gives us even 4 from here.
Yeah, so it's basically, as you say, from increasing, like second successor, it gives you the second predecessor.
Yeah, it gives you the argument that might create.
Argument, yeah, exactly. Arguments of this constructor. Okay.
So the way I see it is, this is a very slight automation, and you do not have to really remember the name of the constructor. Is looking for the constructor name. You have a slightly more high-level proof, or say a more portable proof, because this proof could be, these steps could be applied for other proofs as well, and you do not have to remember how this plus 2e, this cop is the inversion techniques does it for you.
Okay.
Inversion, it feels like inversion just says that you should fail to prove that.
Okay, we are not yet there.
Hypothesis is true. The hypothesis, we have a hypothesis. So if we go back to the intros, hypothesis says that even 5 should fail, and the inversion just says that even 5 should not be proved.
I don't think so.
Okay, let's continue. Maybe it will be more clear.
Yeah, philosophy maybe.
Okay. Now we have a statement H1 that 3 is an even number, which obviously not true, but we haven't yet proved it. Now we want to inverse hypothesis H1. So the only way to construct even 3 is by constructing even 1. And then we try to inverse H2. And both data constructors of this even data type don't match, because 1 is not 0 and 1 is not the second successor of some other number. And and we actually concluded that our assumptions can't hold, and if our assumptions, what we have above this line, just wrong, then we can prove anything.
Sorry about asking this, but how does the machine know that there is no number that is before 1?
Because
Just based on
based on our definition of natural numbers. So
1 is defined as the successor of 0.
yeah, it's S of 0, and S of 0 is definitely not S of something.
One is just syntactic sugar.
Yeah.
All the numbers we see are just syntactic sugars for this version.
It's going to find the pattern that matches. That's
kind of.
I think the what you described as unification. It tries to apply unification to all possible patterns, like pattern matching. There are some crazy proofs that show that these, just looking at the symbols is enough to make them conclude that it's impossible to construct a symbol.
Okay.
Very similar to the thing above, where you said just say constructor. I think the version is the same, just but not for the line below, but for the stuff above the line.
Sorry, I can't comment about unification. I don't know much about unification and stuff. Can't comment.
You have to learn Prolog.
Yeah.
And then you understand that.
Okay.
Also, if you know C++ templates, you probably already know what unification is. But templates are going only one way. I think.
Okay. Sorry, we are running a bit out of time. I have some more material, so we can discuss it afterwards. So you could ask what false means. So it definitely not the false as a value of type Boolean that we introduced before. It's a kind of special data type in Coq. Let's print it. It's just a regular data type, but with 0 constructors. So you normally have no way of create of a value of type false. And going back to our goal, so we want to disprove that 5 is even, and instead of that, if you prove that if 5 is even, then we can construct a value of type false. But since it has no constructors, we can't construct it. And if we prove it, that it means that we couldn't have a value of type even 5 in the first place. That's a consequence of this Curry-Howard correspondence. So negation of some statements in the world of mathematics corresponds to the type from this statement to an empty type with no constructors. So whenever you want to prove some negative statements, just take original statement and construct a function from this to an empty type.
And how would you prove that one is
Sorry?
How do you prove that 1 is not even without tech?
Actually, I will answer this question a little bit later, probably. Okay. Then let's go back to slides. And the final part of my presentation is actually the most important. It's about induction in Coq. How many people know about induction in mathematics in general? Yeah, that's great. So, mathematical principle in induction for natural numbers says that if you have some predicate which depends on natural number, and you can prove that it holds for 0, and also given that it holds for a particular natural number, you can prove that it holds for the next natural number, then this predicate holds for all natural numbers. Let's apply it to our natural numbers. Let's declare the most simplistic theorem for natural numbers which involves induction. So let's prove that if you add 0 to a natural number, that then it doesn't change. Okay, so you can see the goal on the in the right corner, and let's apply tactic induction for the variable n. So now instead of one goal, we have two sub-goals. The first sub-goal corresponds to the base case of induction. So the statement for n equals to 0, it's exactly the same. And the second goal is the statement of induction step. Okay, let's focus on the first goal. It's obviously solvable by auto tactics. And now we focus on the second goal. And you see, we not only have to prove this statement for the next number, but we have this statement for the previous number as an assumption. Here. What is above the line, we can use as assumptions. Okay, let's simplify this expression. Okay, then I use one more new tactic called f equal. So it's basically a functional equal. So you have the statement about equality of the result of function s. So you have s applied to n plus 0 and s applied to n. If we can prove that arguments of a function are equal, then of course the results of a function for those two values are also equal. That's basically what f equal tactic does. It just eliminates this s. You see? Okay. And now our goal looks exactly like our hypothesis that we can apply. That's it. Now I could use this lemma as a step to prove a more interesting fact that a plus b is equal to b plus a, but we are running a bit out of time, so it's not really important.
Just a comment. We have time, I guess. There's no strict limitation.
Yeah, but you have...
Unless you're running out of time. So. No worries.
Okay, thank you, but still I respect kind of powers of your body and engagement. Okay, but natural number is only a particular type, and we want to apply such inductive reasoning to more interesting types than natural numbers. So, for example, let's declare data type tree. So it's like tree from job interviews from Yandex. So you have a tree of natural numbers which has two cases. So it's either an empty tree which has no elements, or it is a branch. So you have a root which holds a natural number, left tree and right tree. Yeah, so it's a data type with two constructors. And let's declare some recursive function on it. Let's try to implement the insertion into a tree. So we take a new natural number, and then if it's smaller than the root of the tree, we insert it into the left part, and otherwise we insert it into the right part. Here is the definition. So we again do pattern matching on the tree constructor. So if original tree was empty, then we just create a tree with only one element. If it's not empty, then first we compare our new value with the root. And in one case, we recursively insert it into the left tree. And otherwise, if it's greater than the root element, we insert it in the right tree. So you see that when we declare a fixed point, we are allowed to recursively call this function on a structurally smaller argument than our original argument. So if we create a function for a tree, we are allowed to call it for a left subtree and for a right subtree. The same we did when we declared a function on natural numbers. When we declare a function on successor of n, we are allowed to use the result of function from the predecessor of our value. That's how recursion works. And if you think about induction, it's basically the same. When you want to prove some fact about a natural number by induction, you are allowed to base your reasoning on this result for the previous number. So the same works for trees. Let's prove some fact. So now I want to define one more property that a natural number is somewhere inside this tree. I mean either in root, in left subtree, or in right subtree. Again, these data types will have three constructors. So first possibility when the number can be in this tree if it's exactly in root. So it takes arbitrary left subtree, right subtree, and creates the fact that number n is in a tree with n as a root. The second constructor says, it's called in left, and it says that if you have a proof that n is in left subtree, in some tree, then you can pick arbitrary right subtree and arbitrary root, and it will be in a bigger tree. And the third constructor is the same. So you can take a tree, consider it as a right subtree of a bigger tree. And if you can prove that n is in this tree, then it indeed in a bigger tree.
So this proof works assuming that our tree is really a binary tree.
No, actually here it doesn't matter. So we can insert this way even if our tree is not a search tree.
I mean, what if we have more than two subtrees? I mean, like, this works if the tree is really binary tree, but what if our tree has more than left and right subtrees? What if it has three subtrees? Like,
then it would be a different example, different task. Yeah. I take the most simple example as possible to just show you how structural induction works in Coq.
okay, well,
So it's not about algorithms at all. Hate them. So, and now let's prove a theorem that if we take a tree, then insert some value into it, then this value will actually be present in this tree. So here is a statement you can see in the right that we want to prove. And let's again apply induction tactic. So 3 is not a natural number, but still Coq allows to use induction for it. And we have two cases. So because tree has two data constructors, we have two cases. So first case corresponds to an empty tree, the same as base case with n equals to 0 for natural numbers. So now we have to prove, so we have a tree with one element in the root, and we need to prove that this element is indeed there. Okay, we apply simplification, and now apply actually this constructor corresponds to in root constructor. Okay, base case is proven. Okay, and then the second case. We now our tree is a non-empty tree with root left branch and right branch, and we need to prove the statement. But you see, now we have two hypotheses that we can use for the left subtree and the right subtree. Sorry, can't. Sorry. But you see, HTT1 is exactly the statement of our theorem applied to the left subtree, and the second is the statement of our theorem applied to the right subtree, and we can base our reasoning on top of that. Okay, let's simplify it. Now you see that our goal became a little bit ugly, because now we need to consider two cases. If our new element is smaller than a root or bigger than a root, then we do case split on this. So two cases, if it's smaller or it is bigger. Then we focus on the first case, when we actually want to insert in the left subtree. But this statement looks exactly the same as our induction hypothesis for the left subtree. And we apply it. No, sorry. We want to prove that n is in our big tree by proving that it's in the left subtree. So we apply the first constructor in left for the in property, and after that it looks exactly like our induction hypothesis, one of them. And this case is done. And now, if we consider the second case, we are inserting to the right subtree. We apply an in-right constructor, and then our goal looks exactly like the second induction hypothesis. Okay.
These induction hypotheses, are they defined before? Or
No, this is what Coq generates for us. I will tell you right now about it.
It's predefined names Coq uses. IHT1, IHT2 is generated names for these
It's auto-generated names, but you can specify them themselves if you like. But by default, it's just assign some fresh names.
Okay, there's some naming algorithm.
Yeah.
Just give it these names.
Yeah.
IHT.
But normally people who care about names, they can specify it. So you can say, I apply induction tactic, and please call my induction hypothesis like that.
So these are just default names.
Yeah.
Just one question. Maybe it's worth doing a small break. And
I'm almost done.
okay.
Yeah. Okay, so now I want to disclose the magic behind those induction principle, how it works not only for natural numbers, but for all recursive data types. So whenever you define some inductive data type, Coq generates for you some support functions that helps you to both define recursive functions and define and write proofs by induction. The most important of them is int function. So we declared data type net, and Coq automatically generated for us a function called netInt, natural induction. Let's check this type. So please look into the right bottom corner. So it says that for arbitrary predicate P, you can prove that P holds for all natural numbers if you can prove that it holds for 0, and if you can prove that it holds for next natural numbers based on the fact that it holds for the previous one. So it's exactly how mathematical induction for natural number works. Let's check what it generates for our tree data type. So again, it says that you can prove some predicate for arbitrary tree if you can prove that it works for an empty tree, and given that it works for left tree, and given that it works for right tree, you can prove it for branch consisted of some root, left subtree, and right subtree. So that's why there is a keyword inductive. So all this machinery based on this inductive data type, and the theory behind Coq is called calculus of inductive constructions. So it's basically the formalization of how this language creates induction principles for your recursive data types. So it takes the definition of your data type, looks at its shape, and evaluates how induction for this data type should look like. So
Derives it from the shape of the data type.
Yeah.
The induction.
Yeah.
And therefore it says that there is a, so it's, as I see it right, it is a function with two arguments. First argument is the predicate is empty. Second argument is the whole expression beginning with for all, ending where you have highlighted the thing. Then there's another error, and the result is another for all. So that's the property for all t's.
Yeah.
That the for all trees that this property holds. Yeah, for any tree.
Yeah. So tree has two data constructors. Then tree induction will force you to prove two cases. So for empty constructor, you will have to prove that P of this empty works. And for the second one, yeah, you have to prove it for branch and can rely on the fact that it works for subtrees.
But as a whole, it can be seen as a function with two arguments?
Yeah, yeah, yeah.
Result is
Yeah.
the proof for the whole.
Yeah, carry forward. Everything is just a function. Yeah. So induction is just a function.
The 3 arguments, because the first argument is the proposition, the P.
Yeah.
Is the,
Yeah.
the proposition you want to prove, then
Yeah, strictly speaking, yes.
I got a question, I'll probably put this into the next galaxy. But this seems like it would be a very powerful tool to, say, prove algorithms. And the first one that came to mind was red-black tree. So how tough would it be to use coq to prove red-black trees?
So please go to this course, and in the end of this course, you will be able to prove it exactly for red-black tree. It's not very easy. I skipped this exercise.
That's a great idea.
Okay, so just one more example of inductive data type. Let's define a list data type. So it's something in between natural numbers and the trees. So it has 2 data constructors, nil, so empty list, and cons, so concatenation of an element and the tail of the list. And let's see which induction principle it generates. So again, so to prove something for a list, you need to prove it for an empty list, and to prove it for a concatenation based on this proposition for tail as an assumption. Okay, and also it works even for Boolean. Induction works even for Boolean data types. So induction principle becomes very trivial. So to prove something for Boolean, you have to prove it for true, and you have to prove it for false. Yeah, so it's a degenerate case of induction. Okay, and let's check that when we prove something using tactics, that it actually uses this induction principle underneath. So we remember that when you prove something, it's just a function. So we can print it. So before we proved the fact that if we insert something into the tree, then this element is indeed inside the tree. Let's print this proof. Okay, you see this proof in the bottom corner, and it's quite long. But the most important thing is you see that somewhere in between, you see the call of function treeInt. So underneath, it just uses this machinery. No magic. Okay, I guess we are done for today.
Would you try please to export this, these programs, so to say, into Haskell or Ocaml? I mean, like just to see how
right now, no, it's not one-click action. Yeah. So this is one of the problems that I will mention right now. So let's make an overview of why it's useful or useless.
Is it still human readable?
I guess yes, because this Coq language is quite close to Haskell and Ocaml, so it's just the same, but with proof erased. So
it's not an assembler code or something. Well, yeah.
For some people, Haskell is assembler code. So
I mean, well, yeah. I mean, it's not just like letters all over the place and plus minus and
basically, you are not supposed to modify it manually, because if you modify it manually, you lose all because you lose all proofs. So you prove something, but then run some other code. So why not just run it directly in Haskell? So the point is just use it as a black box.
Well, the motivation is like, I create my program in Coq, export it to Haskell, and then I just tell my colleagues, okay, here you have it. Have a look at it, have fun. And I don't need to mention Coq or anything else. Don't need to bother my colleagues with something.
No. The idea is you export it into Haskell and then compile it with GHC and just get binary. If you have some manual interaction into the source code produced by Coq, you lose all guarantees, right?
No, he doesn't want to modify it. He just wants to.
Just want to like to show my colleagues, tell them, okay, here you have it. Like have a look at it. Try to find some mistakes. I know that there are none, but I don't want to tell them that I was doing it using Coq.
Okay.
Keep your colleagues honest.
Okay. I don't think it's the best way to create Haskell jobs. So.
It's just meant as a function composition, a function from Coq to Haskell and a function from Haskell to binary, and you compose it and you forget the Haskell, which is intermediate.
Okay.
That's, I think, how it is meant, as he says.
So let's compare Coq to other techniques in formal methods. So if you compare it to static checkers, so the advantage or disadvantage that proofs and actual programming are done in the same language. So you don't need to program in C and then additionally verify it in some commands in some another language. So if it compiles, then it's correct. So it's the same language. So
No more tests.
yeah. If we compare it to model checkers like TLA+, so the first advantage is Coq type system is powerful enough to prove every theorem you can imagine. So of course there are limitations, but it's the same theoretical limitations like philosophical limitations of mathematics in general. But whatever you can prove with pen and paper, you can prove with Coq. So no need to like do an exhaustive search like in TLA+. And the second most important advantage for me, like an industrial programmer, that there is no incoherence between the model and the implementation. Because I don't launch rocket to the sky, I do, I don't know, online advertisement, and I don't have a privilege to run some model checker, create model checker for months, and then additionally run implementation. I have constant change of requirements, and I want my model be always coherent with the implementation, because it's more likely to create a bug when you implement it. And with Coq, your model and your implementation, if you use this extraction into Haskell or a camel, they're coherent just by construction.
You know other programming languages which you can do that, or is Coq the only one?
There are, so the camel is the most mature. Haskell mostly works, and also there are I read that there are experiment backends in Scheme, but no mainstream languages like Java.
Okay, you're asking about
I
generating.
didn't expect that.
Did you ask about extracting to OCaml or
No,
Coq?
the possibility to prove.
I think you mean things that are similar to Coq.
Yeah.
Yeah.
Right.
I think you asked it. I heard of Agda.
Yeah. Can do it.
Yes, so yes, it's just a little bit out of scope comparing different verification tools, but so Agda is quite similar. It has no tactics, so if you want to do some mathematics, it's more suitable to use Coq, but Agda is closer to programming. And the most promising new generation language is probably Idris. So the idea of Idris is to bring all this theory and machinery closer to our day-to-day jobs.
How is it called?
Idris.
Idris.
IDRIS. Okay.
So it's a hot topic today in functional programming community. Yeah.
Are there certain requirements for the programming language they must have to be able to do that? So, for instance, recursion, that's clear, but for instance, dependent types is a precondition to do proofs.
If we are talking about carry-over correspondence, then your host language must be powerful enough to actually map all properties they're interested to some types of this language. So basically, yeah, it means that it at least need to have dependent types. So if you want to prove something about natural numbers, then you need to somehow encode natural numbers in a piano way. Then you need a predicate to be able to define to depend on a natural number. So basically, it means dependent types. And also, it needs a totality checker, because if you allow your recursion to non-terminate, then you can prove everything, and it's unsound.
The example is natural numbers and with generated functions like net_int. So it felt like you can just avoid the inductive, like the type definition, but you can just define the functions manually, or would it not work?
But how do you guarantee that your manually defined function is mathematically correct? Here, it's Coq generates it for you, right?
Yeah, but it means that you can also write it by hand, right?
I don't think so, because I think that if you write it as a programmer, you have no way to prove that it's well defined. So it's some meta level. So it's based on the theory behind the Coq that such functions like not_int are well defined. So you're not supposed to write it as a programmer.
Yeah, I'm just trying to understand what does it mean to for a language to support dependent types.
No, dependent types is another topic, so it's a precondition for allowing induction. But it's basically dependent types. So normally, I don't know, in Java or whenever you have just a types like string, integer, it's just a plain type which contains values. Also, you have type constructors like list. So list is not itself a type. So list of strings, string is a type, list of integer is a type. So list is basically a function from type to type. And dependent type allows your types depend not only on another types, but on values. The most classical example is a vector of fixed length. So for example, you can have vector, vector, so it's a list of a fixed length. Yeah. So if you want to have a, I don't know, list of strings of length 3, it depends on the string and depends on 3. But 3 itself is normally in normal languages is not a type, it's a value. But you still allow your type vector int 3 depend on values.
So a variable list could not be a type. That's basically what you're saying. It has to be fixed.
List itself is not. Yeah, it's not a type. You need say list of what? List of strings, list of integers.
Yeah, but it also has to be a set length. So you have to say a list of 3 integers.
Yeah, and if you define a list of a particular length, it depends on the type of the content and on the length.
So you couldn't just leave it arbitrary. A list of
But that's a different question. Sometimes you want a fixed length. So you want, for example, to say I have a list of length 3, list of length 5, and when I concatenate them, I am guaranteed to have a list of length 8. Okay. You can't achieve it with a list of arbitrary length. So it's sometimes useful. Okay, so and okay, let me just finish and yeah. So the problems with such theorem provers, first is they're quite hard. So you can't learn it and start applying it on the second day at your job. So second, you can't reason about space leaks and garbage collection. So you can reason about some properties of your model, but can't directly reason about how your program actually runs. And it extracts into the languages with a garbage collection, and so you probably can't build real-time systems with it. And the third problem that, okay, we can prove many things about mathematical numbers, but those ideal mathematical numbers are very poorly mapped into a hardware. So, for example, if you have overflows, so all statements from mathematics just don't hold. And we are not even talking about rounding errors of real numbers. So, for example, when people written this certified C compiler, they map natural numbers not into like natural numbers, like 4-byte, 8-byte. They map it to those piano numbers. And not surprising that for huge numbers it can just blow up in runtime.
I would imagine you also have difficulty mapping, say, rational and irrational numbers. You couldn't do it with this, could you?
So you can map. Real numbers in Coq is a kind of hard problem because it's hard problem in math. What is a real number? Real numbers are kind of, it's not directly constructive. So so you have to factorize some sequences by some real equality relation. It's not that easy. But even if you map, you just lose all mathematical properties, right? Because of rounding errors. So it's just impossible to map some set of infinite space to a set of finite space.
Is there certainly a problem with floating numbers then?
I would say this is not quite true. In the Coq library, there is a formalization of real numbers.
Yeah.
So you can prove statements about real numbers.
So yeah, you can prove, but when you map it to a hardware floating numbers, you lose all those proofs.
I think I don't know exactly the restrictions about extracting programs to kernel. I think not every Coq program can be extracted to kernel. I'm not sure. But there is there are also the Coq library support for 64-bit real numbers, so you can prove things about them, and you can for 64-bit integers. But these are separate theories.
Yeah, thank you.
What about a proof that Coq works properly? I mean, well, probably it's too complicated. So, if you find a bug, how do you address it? Like, how do you deal with existence of bugs in Coq itself?
You go to GitHub bug tracker.
Yeah, but I mean, well, basically, you use Coq because your software is running somewhere around mission-critical systems, and you really want to be sure that everything works. And all of a sudden, you find a bug.
I don't know. You pray. So at least you will have less errors than when you prove it with pen and paper.
No, I think he's asking about what is the assurance that the machinery behind Coq is correct. So what I understood is there has been PhDs and published papers about the theory on which Coq rests, that they have been published and reviewed, and at the core of Coq is the type-checking algorithms of the proof terms. And the way I understood is that this algorithm is small. It has been verified, so it's relatively small. That's what I understood. And therefore, people are relatively sure that there are no mistakes in this type-checking algorithm. And the type-checking of the proof terms is the key.
So if there is a bug, then typically it's a bug somewhere in the interface or something like that.
Yes, yeah.
There were some bugs reported, like so. I mean, there are no guarantees. There are bugs, and like as in all the software, but it probably better prove that your software works if you use Coq than use like C or whatever other language.
I think we should
Okay.
Take it offline.
Okay. So
No, just to add that you can, I understood the question, I think normally you try to teach the code, right?
Okay. So thank you for your attention.